So I think we are ready to start. Hello, welcome to our webinar on AI for the Access to Space for All initiative. My name is Hazuki Mori of the United Nations Office for Outer Space Affairs, and it is a pleasure to have all of you here with us today. First, before we start the webinar, I'll be explaining some logistics. So as you can see in the screen, first, please make sure to turn off your cameras and your microphones. Second, there is a chat section, so please use the chat for any questions or comments that you may have. We will have a Q&A session at the very end, and we will make sure to collect all your questions and make sure to answer them there. So please make sure to write in your questions in the chat. And third, we will post a link to our questionnaire for the webinar. So please make sure to answer the questionnaire before you leave the webinar. All of your feedback is very important to us. And also, if you sign up for our distribution list, we can send you more information about the activities we do in UNOOSA, about webinars, events, and stuff like that. So please make sure to answer the questionnaire before you leave. Okay, and I hope you can see the agenda. First, we will have Jorge, who is my colleague, introduce you to the Access to Space for All initiative. Second, we will have speakers from IBM talk about their projects. Third, we will have a speaker from NVIDIA talk about their projects. And last, we will have a person from the European Space Agency talk about FieldSat. And at the end, we will have the roundtable and Q&A. Okay, so I think I am already ready to introduce you to our first speaker, who is Jorge Del Rio Vera from the Space Application Sections of UNOOSA. Sorry. Jorge, I will give you the floor now.
Thank you very much, Hazuki, for the introduction. Let me share my screen. Hope you can all see it. So I'm Jorge Del Rio Vera, and as Hazuki mentioned, I'm working for the United Nations Office for Outer Space Affairs, and we have put together this webinar in kind of tandem with an initiative that we have, which is called Access to Space for All, where we are providing hands-on opportunities to acquire access to space capabilities. Before we start, I have a question for all of you. Why should you care? Why should it be important to get access to space for all? And probably you are thinking already about the answer. Let me start with a few facts first. The value of space economy. Today, the space economy is ranging from 350 to 425 billion, depending on the estimate you're looking at. But by 2030, the estimates that we have say that space economy will be valued between $1 trillion and $3 trillion. It's having a sharp increase by several times. Last year it was a very important record for space employment. It got the 8-year high, the maximum of an 8-year period, and it's increasing. I mean, this year, because of the pandemic, there are many sectors that are affected, but that is a trend that will continue after the pandemic. If you're looking at the number of launches, we have seen an average growth of 39% in the number of launches in the last decade. Not only that, last year, there were almost an average of 2 launches per week. I mean, I still remember the times when launches were hitting primetime news. And last year we had like 2 launches per week. And that's, to me, is a very striking fact. There are more than 80 countries that have put a satellite in orbit. I mean, there are countries that have put many satellites in orbit, but more than 80 countries have put at least 1 satellite in orbit. And counting, the number is increasing. And thanks to one of the programs that the office is offering in partnership with JAXA, the Japan Aerospace Exploration Agency, 2 countries have put a satellite in orbit of those 80 countries. So the office and JAXA have contributed to more than 2% there. And there are 95 countries that are members of the Committee on the Peaceful Use of Outer Space. The Committee on the Peaceful Use of Outer Space, COPOS, is a committee of the United Nations where countries are gathering to discuss aspects on the peaceful matters of, of outer space. So there are more than 95 countries. That means that there are countries there that have not put a satellite in orbit. And that's important, because this is showing the interest that the space is having, and it's having an increasing demand. I mean, there are countries that are applying for membership every year. So just to give you, this just gives you an idea of the economic picture and the interest that some countries are having, or many countries are having in space. In the office, what are we doing? We are trying to get these potential benefits that we have seen, and we are trying to promote and to further engage countries and institutions within countries. In the space application section, where I work, we have a number of programs which are aimed at building capacity in countries. So there is not a gap between the countries that have a lot of capacity and countries that don't have capacity. We call that the space divide. Well, we are trying to bridge that space divide so that it doesn't become very big. Space is also important for social matter. It's not only about economy. If you are looking at the most ambitious agenda that has been put by the United Nations, the 2030 Agenda for Sustainable Development, there are 17 Sustainable Development Goals. This agenda was approved in the General Assembly of the United Nations. 193 countries said that, yeah, they wanted to go for it, and entered it more or less into application in 2016. If you look at the goals, the 17 Sustainable Development Goals that have been put as goal for 2030, you see things like no poverty, zero hunger, quality education, and a lot of very important things for the world of today. But the Sustainable Development Goals as such, I mean, it's very difficult to say, okay, no poverty in this country means this, and in this country maybe it's something different. I mean, it might not be the same from one country to another. Well, to solve that, under these 17 Sustainable Development Goals, you have 169 targets that have to be achieved in order for the goals to be achieved. And under that, there are 231 unique indicators that are measuring the progress towards those goals. That's important because in this program, in the Access to Space for All, we are asking that when we are getting applications for an opportunity, that the application is connected to the Sustainable Development Goals. And we have demonstrated in the office that nearly 40% of the targets can be supported by Earth observation and global navigation satellite systems alone. Imagine if you include other space technologies. And space is also playing a fundamental role in education. It's a very inspirational tool. There is this Sustainable Goal number 4, quality education. Below that, you have one of the targets says, by 2030, substantially increase the number of youth and adults who have relevant skills, including technical skills. And that's where space comes into play. So you have not to look at the goal, look at the targets. You will get a much better picture. So space is playing a very significant role also for societal benefits. And this initiative in particular, well, I talk a lot about the initiative, but I didn't describe it in full. It's aiming at providing hands-on opportunities. We are focusing on hands-on opportunities to access either research facilities or infrastructure that otherwise will be too costly or too difficult to access by some institutions in some countries. So we are trying to ensure that the benefits of space are accessible to everybody, and they are competitive opportunities, and you will see the list of opportunities in a while. As I said, the office has been providing theoretical capacity building for a long time. We have provided that since the establishment of the Program of Space Application that was established in 1971. And we are continuing to provide that because that's an important pillar. But still, today, in the world of today, you have to provide hands-on opportunities so you experience actually what it is to build a satellite, what is it to put a payload in microgravity. As I normally say, you cannot learn how to ride a bike by reading a book. It's as simple as that. And how is the initiative looking like? Well, the initiative is, I'm sorry with this slide. Okay, this is small hiccup. Okay, here we are. This is how the initiative looks like today. We have 3 different tracks that are designed to build capacity from A to Z. The track on hypergravity and microgravity, which is designed to build capacity in building a microgravity payload, so putting a payload in orbit, an experiment in orbit. The satellite development track, which is aiming at put a satellite into orbit, and the exploration track. You see that there are some gaps there. Those gaps are opportunities that we think that they are important to build capacity in a gradual way, but we still don't have a partner. And as you can see there, this initiative is relying a lot in partnership. You have partnerships there from space agencies to research institutions to private companies. And we are working to bring more partners into the Access to Space for All initiative because we cannot do this without the partners. We don't have infrastructure or facilities to offer. And we are actively working in solving those gaps to provide this gradual capacity building. So we also see that it's important to have theoretical capabilities, and the Program of Space Applications is delivering that through the webinars and courses. But for Access to Space for All, we have organized this series of webinars, and the example of today is one of them on artificial intelligence and access to space. But we have more. We have, for instance, webinars that are coming up about KiboCube, which is the opportunity that we are offering together with JAXA into putting a satellite in orbit from the International Space Station. And in that series of webinars, we will open the opportunity very soon. I believe next week, we'll do the announcement opportunity. Then we will have a webinar on how to improve the application form, which are the key elements that have to be considered for the application form if you want to actually design and implement one new CubeSat and deploying through this opportunity. And on top of that, we will have the KiboCube Academy, which is a series of webinars that are specifically designed to give you an overview of the process from design, testing, and implementation of a CubeSat. So we are building capacity also in a theoretical manner under Access to Space for All, but it's everything aiming at the opportunities that I mentioned before. Some practical examples. These are some pictures of the winning team of this year of an opportunity that is called Drop Test. We are offering this opportunity in cooperation with CERN, the Center of Applied Space Technology and Microgravity in Germany, and the German Aerospace Center. And it's about the utilization of a drop tower that exists in Bremen to simulate microgravity. Well, there was a team from the Universidad Católica de La Paz de Bolivia, from Bolivia, and what they are proposing, what they are building now is an extruder to test a new 3D printing technique in microgravity. And they are building the extruder as we speak, and they will be testing that extruder in microgravity next year, in the microgravity in the tower. And this is something that is very important because the skills that are acquired through these programs and through these opportunities can be applied to something different. I mean, it's engineering, science, technology, mathematics, the type of skills that you are acquiring. And the team that we got this year from Bolivia actually was involved in the development of a low-cost ventilator that has been used in Bolivia for fighting the COVID-19 pandemic. I'm not saying that it is because of Access to Space for All. not at all. But what I'm saying is that when you have the set of skills that are allowing you to put a payload in microgravity or run an experiment or create a CubeSat, you can apply those skills for something else, like building a low-cost ventilator for fighting the pandemic. This year also we have the launch of the first satellite of Guatemala. That was thanks to KiboCube, the opportunity that we have in cooperation with JAXA. And the satellite is up there and is already providing data down to Earth. So we are also very proud. And as I said, we will open a new round of KiboCube next week. So stay tuned and to get more information if you want to apply to something like that. How can you help us? Because I mean, we are doing this in cooperation with partners, but we still need help. Sometimes the information about these opportunities don't get to the people that actually can apply to them. We are having a very intense campaign in social media, but if there is one thing that you can do for us is please use the hashtag #AskSpaceForAll in your social media so people get related to the opportunities that are available. And we are opening opportunities on and off during all the time of the year. So this is very important for us to get to those that can take advantage of these opportunities. Sorry, I'm going backward. And then, I mean, this webinar of today is about the role of AI and access to space for all. And here you see the opportunities. I'm going to show you one video about drop test, which is an opportunity in the hypergravity and microgravity track, as I said, in cooperation with DLR and SARM. And it's about this drop tower. And the video is about an experiment that was run by students in Costa Rica in 2016, and they were testing the behavior of robotic arms in a microgravity environment. So what you see there is two robotic arms that are moving around. Of course, it's dropping, so at some point the robotic arms will go down because of the deceleration. But they were gathering data about this behavior of the robotic arms. Imagine, I mean, if you want to incorporate artificial intelligence to a project like this, you can train a robotic arm on ground and then put it into the microgravity conditions that a drop tower can offer and see the behavior and see if you can incorporate adaptive behavior to the robotic arms. So the possibilities and the potential are many. I mean, if you're looking at the news, and you will see in the presentations that are coming after, artificial intelligence is starting to be all over the place. It's been over the place for a while, but now it's more over the place in space than ever. And there are a number of projects that are really highlighting that cooperation, and you will see the presentations later on. Artificial intelligence is a lot about hardware, software, it's computing power, it's also about data. If you think in the amount of data that is generated in the International Space Station, there are 28 terabytes of data generated every day. That's a lot of data, and you can actually train machine learning models with the amount of data that is generated by the different probes, satellites, rovers, and the International Space Station that is out there in orbit already. So we want to also incorporate the aspects of artificial intelligence. We will be very much appreciating proposals to the opportunities that are incorporating artificial intelligence, because that's important for us. I was talking before about this space divide, so the gap between countries that have capabilities and those who don't have capabilities or are emerging in the capabilities. Well, artificial intelligence has the transformative potential of widening that gap. I mean, it's happening in other areas of engineering already, so space will not be any difference. So if we are incorporating these areas there to the opportunities, to the proposals, to those students or professionals that are applying to the opportunities from developing countries or for emerging spacefaring countries, that will be a big win for us. Thank you very much.
Thank you so much, Jorge. Now we are excited to bring in the speakers from various different countries and companies. So first, I'd like to introduce two speakers from IBM US, who are Naeem Altaf and Colin Alstad. Naeem is IBM's distinguished engineer and space tech, and he leads the innovation group. He does many different things, like innovating from edge computing in space to supply chain optimization for space assets to autonomous cognitive framework for CubeSat swarms to growing challenges of space debris and collision avoidance. So the list goes on, and it's really amazing. And he has been with IBM for 20 years, and he was recently appointed as technical advisor and board member for Explore Mars. And for Colin, he is a senior data scientist in IBM's Blue Tech Innovation Lab, where he focuses on various applications of machine learning and applied mathematics to problems in the commercial space industry, ranging from satellite image analysis to astrodynamics. He has over a decade of experience in the data science and applied research fields. So I am happy to bring in Naeem and Colleen. Yeah, both of you have the floor.
Thank you very much, Hazuki. Let me share my slide.
While Naeem is sharing, I have been putting some links in the chat. If you have any questions or comments, please make sure to write it in the chat. We will answer them all at the end in our Q&A session. Okay, it looks like it's ready. You have the floor.
Thank you so much. Hi, everyone. Thank you so much for joining this webinar. So let's start. Just to add to what George was explaining, right? So in the last just few years, a lot of activity is happening in the space, right? You see almost twice a week, the SpaceX sending and other manufacturers, rocket launchers sending stuff in the space. And these mega constellations, which will be, already started with Starlink and more to come. And then these are the private-public partnership, right, where we saw the SpaceX Dragon taking the astronauts to the space station a few weeks ago. So yes, a lot is happening in this area. So IBM has a long history in space, all the way, starting from the Apollo missions, sending men to the moon, and that still is regarded as one of the great engineering feats in the history. So what we are doing, so let me take you through a few projects where we are working. So one is the edge computing in space in general, but the project we just finished was on the International Space Station. So on the space station, there is this DNA sequencing project, which uses MinION devices. And the goal of this was to identify the microbes from the surface inside of the space station, and then run through the diagnostics and then bring the results down to the Earth. And this whole process several weeks, if not few months, to get the results into the hand of the principal investigators who requested this thing for. What we did in the partnership with the HPE, that we took the code and we containerized it, and we ran this on the Red Hat OpenShift, the code-ready container cluster. It's a single node cluster, and we put this on the flight systems, which are, this is supposed to fly on February 1st, 2021. So all the testing, everything is done. The systems are loaded with this platform. And basically, when the next time, in February or March timeframe, we request for a sample, a DNA sequencing run, it will run everything, of course, on the space station. And then the results will come to these systems. And with the containers are running, it will go and run it through the pipeline and get the raw data and run through its analytics and create the results. And this whole process will literally, it will take like half a day, 6 to 7 hours, and then the results will come down to the ground. So we're taking it from several weeks or maybe a couple of months to less than a week. So I think that's where the edge computing, like now, this is the edge of the edges, right? I mean, there's a lot of in the industry, we're talking about the 5G networks, edge computing happening on the terrestrial, but this is now going to space. And I think our friends who will talk about the FISAT, that's another example of. Okay, so next project we are doing is around the blockchain. So the basic principle of blockchain is the provenance, auditing capabilities, traceability, and immutability. Right? These are the key things about the blockchain. So we have done some work with our partners in the areas of satellite manufacturing, and this can be any manufacturing in the aerospace industry, where you have a customer who is requesting, let's say, to build a satellite, and the satellite manufacturer has their subcontractors and other part suppliers, and then you have the the logistics of moving in from moving the stuff from where it's to the launch site, assembly site, and then payload in the loading in the fairing, and then finally launching it up. And then you have the insurance companies, you have the regulatory authorities. So all of these different entities who want to understand the whole end-to-end logistics of this, whether it's satellite manufacturing or you are sending a cargo to the space, that's where blockchain can provide you a full transparency to all these parties to see what's happening along the process. And then the other thing is space traffic management. This is about data sharing. So how different agencies around the globe can share information backed by blockchain, where you have a trust and transparency built in. So you know who is looking at your data, what they are doing. So you have a complete control over that. The next project is the KubeSat Cognitive Autonomous Framework. So we open sourced this project in October. Basically, the idea behind here is the CubeSat, right? I mean, we are seeing a lot of stuff happening with CubeSat because they're, relatively cheaper, easier to build and launch, right, compared to your larger satellites. The analogy, if you are familiar with what's happening today in the cloud world, we call it like the cloud native or microservices, where instead of having a big monolithic product, you have several small products, which are basically different functions of that big product, and they're all independently running. And it's much easier to, build and run them instead of sending one big monolithic thing. So our idea here was, how can we, the things which we have learned for distributed computing on the ground, what if we have the swarm of these CubeSats, and all of these CubeSats are loaded with sensors, and they can act totally independent, autonomous, or they can work in a swarm, right? So for example, a request comes in to go and look at a big hurricane which is forming in Atlantic and follow that. So these a request comes in, and we have this messaging service which we built on top of nats.io, nats.io. It's another open source product, which is a very fast, lightweight messaging service. So basically, based on the messaging among these different CubeSat, it can determine who have the resources to basically create a virtual cluster and start tracking the payload which they just got. And once the work is completed, they can release the resources. So very similar to how we do the HPC or the clustering on the ground. How can we take this concept into the CubeSat world and see what can be done there? So the project is open source. You can see the links down there, or you can even look at the demo, which is running at cubesat.space. And hopefully, as you talked about the Cube project, right? Maybe later on we can do some partnership and take a look at this stuff. All right, next slide is I'll let my colleague Colin take you through the space social awareness. Colin, please.
Thanks, Neem. So as I'm sure everyone is aware, detecting, identifying, and tracking all the objects in orbit around the Earth is a difficult problem, and it's only going to become more so with the increasing number of launches and satellites deployed, especially in low Earth orbit. To that end, in collaboration with the University of Texas at Austin, we've open sourced a machine learning pipeline to improve the predictive power of orbital mechanical models to determine where objects are going in the future. So this kind of works by using historical data that in our open source version we get from the Space Track API from US Strategic Command. We then use your given physical model of choice for orbital mechanics to use that historical data to understand where the physical model gets its orbital propagation predictions wrong. And then we can use that to build training data for a machine learning model that it doesn't have to learn all of mechanics, orbital mechanics. It just has to learn where, a given physical model is producing errors. And then the idea is that we can combine these two methods to increase the predictive power of the physical model by, first predicting where the physical model says a satellite will go, and then estimating the predictive error using the machine learning model, and then we can combine the two into a more accurate picture of what the situation will look like in the future. And then if we can go to the next slide. So once we have these predictive, once we have this prediction window, what we can do is, ask questions along the lines of something like, for a given object that I'm interested in, what are the closest things that are going to come close to that object in, say the next week. Or we can say, what things are going to come with some radius of this, and this is becoming a very needed problem, like we've just seen, like last month in September, at the end of September, with the International Space Station having to move at kind of the last minute out of the way of a Japanese rocket body. So these are the kind of tools that we've open sourced to sort of help aid in this problem.
Awesome. And I think, George and Suzuki, that's all we have. These are the 3 or 4 projects we wanted to share with the team.
Thank you so much both for your interesting presentation about the projects that are done in IBM. I think there's a lot that people can learn from this, and it's definitely low cost and efficient. And also, a lot of the tools were already open source. So anyone who is interested in applying to our initiative, using it in our initiative and to others, I think it's a really great information for all. So thank you so much.
That's welcome.
Okay, next I'd like to move on to introduce our speaker from NVIDIA, who is Allison Lotus. So Allison joined NVIDIA 5.5 years ago, and she spent her first couple of years as a deep learning solutions architect, and she is now responsible for NVIDIA's artificial intelligence developer relations across the EMEA region, which is Europe, Middle East, and Africa. And yeah, she consults on a wide range of AI applications, including planetary defense with NASA and ESA, and she works closely with the community of AI and machine learning. So the floor is yours, Allison.
Okay, can you hear me and can you see my screen?
Yes.
Yep, we can see you loud and clear.
Wonderful. Okay, fantastic talk, Naeem and Colin. Thank you so much. So this is me. I'm based in the UK, clearly, and I've been in NVIDIA for a time that's actually quite unprecedented. Nobody has ever seen the kind of technological progress, and not only in space, but my field is artificial intelligence, and to see the progress that's made, which is just insanely rapid. Anyway, first of all, I just wanted to do a shout out for the Changi 5 team. I was glued to the screen yesterday. YouTube actually went down at 1440, and then the Chinese streams went down, and coverage was actually never regained. It was so frustrating, but in the end, it went well. Changi 5 successfully landed and is currently picking up regolith, and tomorrow goes home. But this is, very impressive. 8th craft sent to the moon by China. 8 crafts. Again, just so much activity. We the general rhetoric is, it's been ages, 69 since we went to the moon, but there's so much activity. We've had constant humans, on the ISS since that time. But the new year will bring years and years of continued activity on the moon. 5 attempts to land that I know of in 2021. India and Israel will retry. They both unfortunately had failed landings recently. But luckily, we innovate fast, we fail fast. This is the Silicon Valley way, and we learn fast. And it's hard to believe that when I joined NVIDIA, such a short, time ago, researchers were only just starting to link 2 GPUs together. Picture there of our server form factor, for those that don't know what a graphics processing unit is. For my research, I was actually granted a Kepler 40 that had 12 gigabytes of memory on board, and it was fascinating. to be able to have that much. But now we have 80 gigabytes, which is plenty to tackle the world's most important scientific and big data challenges. Our latest chip architecture, Ampere, has now got 3rd generation tensor cores, and this is what rapidly calculates the core mathematics that drive all artificial intelligence, matrix multiplication and accumulate. You can even partition the cores across multiple independent workloads. And when you pair GPUs into massive clusters, you literally break efficiency records. So this was built in under a month, our Selene supercomputer, and it's now the world's 5th most efficient form of compute. And a particular configuration, something we call superpods, is the #1 on our planet's Green 500. So it's capable of providing just over 26 gigaflops per watt. So that's the most performance out of a single watt of power. So vastly reducing the carbon footprint of this technological progress that we're making. We analysed based analytics of the data we're getting from satellites and spacecraft. This is yesterday's typical data center. This is today's. So 1/20th the power, 1/10th the cost for the same performance. Our software platform also makes it as efficient as possible to deploy. It's all free to access, collections of libraries built on top of CUDA, which is NVIDIA's parallel programming language, providing all of the essential optimizations. So we've done the work for you, and you can access our GPUs in laptops, in desk-side workstations, in private racks, in every major cloud service, all helping to democratize the power of AI. So taking the data and images that we get from satellites and bringing it rapidly to the user. And that's a user, whether it's the United Nations for monitoring the SDGs, to a prime minister or president, or to a farmer in a field somewhere. The Minion device that Naeem talked about can literally be given, it's a handheld small device that runs with our embedded GPUs. And it can be given to non-technical experts to perform this genomic sequencing. And it's quite an interesting, it's an Oxford-based company, Oxford Nanopore, and they're doing extremely well and have done extremely productive and effective work for battling against COVID too. We've also containerized all software for even easier deployment. This wasn't even thought of 5.5 years ago. I know because I personally struggled endlessly trying to link together all the dependent software libraries that I needed to run my code. Resources are here. I'll share these slides on Twitter. But the NVIDIA GPU catalog contains over 100 pre-trained artificial intelligence models, so already done, ready for you to use. But every container, every single asset is validated for performance, quality, and security, and then uploaded centrally to this repository for others to just download with what's called a simple pull command. And Rapids is an open source community-driven library that accelerates all data science. Unfortunately, I don't have the time to do a deeper dive into this, but it's a fantastic resource. There are actually too many software libraries to list, but one that does need highlighting is the fact that we can now use a neural network, so artificial intelligence, to compute pure physics, such as fluid dynamics and wave propagation. Partial differential equations allow us to calculate the behavior of objects over space and time, and calculating these problems over Fourier space, as opposed to the familiar Euclidean, so X, Y, Z, turns out to be 1,000 times faster, with 30% lower. This paper, and the links there at the top, comes in part from our researchers at NVIDIA. Now, this probably, it doesn't look too jittery at the moment. These videos don't tend to work very well over these web, Zoom, etc. Interfaces, but it allows us to do things like this. And this is work with ECMWF, the European Weather Centre, fusing our virtual world Omniverse with HPC fluid dynamics, simulation with rendering, and using our physics engine. So this accurate visualization allows not just scientists, but policymakers and the general public to use this information and take action. This is not just photorealistic, but physically accurate in a collaborative platform. Just like here in Teams, people can meet in Omniverse and collaborate. The entire data set is huge, about half a terabyte per time step, per variable. But we can load it up in regional tiles of just a few hundred kilometers. So it's extremely important for urban planning, for smart cities, for numerous different applications. But what do we really mean by making something physically accurate? Well, quite simply, it means by adding physics to a simulated environment. And with our physics engine, it really is this simple. You pick up an object and apply physics. And that could be any gravity, any different variable. It really is this simple now with code, with graphics, with visualization. Of course, we can't look at the entire globe's weather all at once, just like, our eyes can't see the atmosphere and everything about it. But there are hundreds of little tricks that we can do almost instantaneously. For example, super resolution, or zoom. And that capability is simply code that can be uploaded to any intelligent satellite, which is exactly why large systems integrators are currently launching our embedded GPU range called JETSON into such units. So they're capable of being updated as and when the situation requires it, similar to OTA or over-the-air updates for autonomous self-driving cars. Actually, proving hardware is one of the toughest problems, and NASA will be doing just that in 2022 with the LEO flight test of an inflatable decelerator called an aeroshell, or the Lofted mission. A secondary payload powered by our embedded GPUs, as I said, a product range called JETSON, will be released and separated to record the aeroshell as it actually deploys. But our embedded range is the same hardware built for different use cases. They all use the same software, whether it's for self-driving cars, for robots, for drones, or spacecraft. Xavier includes what we call NVDLA, so NVIDIA Deep Learning Acceleration. And that specifically was open source a few years ago to help standardize inference applications. And all documentation and specs are actually online. The link is there on that slide. One of our partners, OSK, Orbital Sidekick, deployed a JETSON-based hyperspectral imager called HEISS on board the ISS for over 12 months. A second generation is actually going up mid-January, providing a high-frequency monitoring solution for all kinds of users: disaster response, energy clients, agriculture, the farmers that I mentioned earlier. You can see it here deployed. You can just see the unit far right under that platform. This is a picture of San Francisco taken by HEISS in 2019, I think it was. This is East Timor, where you can clearly see biodiversity loss from the hyperspectral imaging. So that's using multiple frequencies of the EMS. So this is our current recommended solution. End of life, I believe, is about 2028. Being deployed in space by multiple systems integrators. We measure capability for AI-based processing in trillion operations per second when we're talking about integer format, TOPS, or floating point operations per second, FLOPS. And unfortunately, there is always that trade-off between power and performance. But here we have the Pascal architecture in a 10 to 20 watt unit, ruggedized for around $800, I think, without discounts. I'm sure we can halve that with discount, and capable of 1.3 teraflops, and that's at FP16, the precision of the compute. Much of the simpler vision-based AI, like the use of convolutional neural nets, ResNets, code like YOLO, etc., can be performed at much lower precision. So going to integer 8 or 4, which basically decreases the complexity and therefore the power and the time to a result. KubeSat uses a tiny Intel unit, actually a sub 1 watt processor that's capable, I believe, of about 80 gigaflops. So that's 3 orders of magnitude less performance, but 1 order of magnitude less in power. With our current acquisition of ARM, the British company, we should be able to move very, very easily into extremely low power processing, and I do look forward to that. This next gen chip that we have now, Ampere, can also add the security of Mellanox, which is another recent acquisition of ours, which brought us the incredible innovation, including Bluefield 2, which is the industry standard for secure high-performance networking. With space applications, we're talking about high-volume streaming data in real time from cameras and sensors. And all of it requires encryption and decryption. I'm currently working with partners who will put the first COTS, so commercial off-the-shelf data center, into orbit late next year, or probably early 22. To be honest, it's not soon enough. I want super pods, on the moon, literally. We've already proven many solutions using harnessing artificial intelligence, but one of the first things I did when I joined NVIDIA is help set up FDL, and Naeem is part of that with me. This is a research accelerated program working with NASA and now the European Space Agency, who hosts the European arm. Naeem actually mentioned space traffic management and collision avoidance. This was tackled this year with a team of researchers and mentors. Last year, we actually automated part of the work of ESA-ESOC, who basically do this collision avoidance by hand for a lot of the time. Pierre-Philippe can talk about that a bit more. We run 2 months long coding sprints, going from idea to tech-ready level prototype faster than ever before. And one of 11 such challenges this year was DTE, or Digital Twin Earth. So here, a team of researchers and mentors focused on predicting extreme rainfall in sub-Saharan Africa. And next week at the World Space Forum by the UN, the FDL director and my colleague Simon Jackman from the University of Oxford will talk more about that to the delegation. This picture is a Ugandan farmer, and the results being presented at NeurIPS next week, and also multiple other AI conferences, are for a 5-day prediction tool, so giving her time to harvest before the actual flooding from extreme rainfall occurs. The team also worked on lightning prediction, which is being presented at multiple conferences, including NeurIPS next week. And remember that lightning causes most of our wildfires. We're all aware that examining Earth is a planetary, at a planetary scale is crucial. And hopefully we're already aware that we've already passed the tipping point for melting of permafrost. We need to stop air pollution. We need to stop biodiversity loss. Monitoring is essential. That link there is Stephen Ramage at GEO, who's set up a website for a lot more information about that. What you're looking at here is through the eyes of an autonomous drone in a forest. This is work by some University of Pennsylvania PhDs that I work with, who've now spun off a company and are currently working with folks like Professor Andy Hector of Oxford in Borneo. This drone is not just capable of cameras like most other drones, but of carrying LiDAR, so exactly what self-driving cars use. Using AI, the drones can literally construct dense 3D maps with centimeter resolution. Couple that with remote sensing from space, and we get highly accurate and very fast insight. But the real power of AI is the capability to train virtual agents in parallel in virtual worlds or in simulation. What you're looking at here is something called distributional reinforcement learning. So learning by extreme trial and error according to a set objective. Here's what we want you to do, figure it out, literally. But thousands of agents all learning together collaboratively and learning in a safe, cost-free environment of a virtual world. Since we can now add complex physics and robotics into a simulated environment or a virtual world, this is some of the results. Work we're doing with BMW and their STR, or a smart transport robot. This was just last month. The unit there in yellow is capable of a 1,000-kilogram payload, and all intelligence is computed on board with JETSON Xavier, and has cameras, sensors, and LiDAR. And it was trained completely in our platform called Isaac, and it's now used to digitally twin their entire production facility in Regensburg, Germany. So the entire facility is digitally twinned, and we can simulate anything from humans. And this is not a photograph. This is a simulated human. It's only a still image here, but we can literally simulate a human to this kind of resolution, to galaxies. And all software to do this is available in that repository that I mentioned, NGC, with code called Cholla by Brent and Evan Schneider, as is mentioned there. So this is a full simulation of the galactic winds of I believe it's the M82. Isaac, the platform itself, is completely free to use. Please go to that website, have a look, download it, get some coders to start playing around in it. And it comes with many different what we call gems, so GPU accelerated algorithms. For example, segmentation of multiple classes, including collision-free space, 3D object pose estimation, stereo visual inertial odometry. Take a look online. Thanks to JETSON, our embedded GPUs and larger systems, we are very, very capable of so much in space. And that was a very, very quick overview. Forgive me for piling on the info. If you want a deeper dive into any of what I've talked about, please get in touch. We have some excellent classes online. So from your browser, teaching you how to build and deploy neural networks using GPUs in the cloud. And we can also organize hackathons too. Do join us for our next conference in spring. And in the meantime, the link there actually includes all content from ourselves, from our partners, available online too. Thank you very much.
Thank you so much, Alison, for sharing the amazing things that are done in NVIDIA. I know that was a lot of information to everybody. Just to tell you, we will put the presentation and the recordings of the webinar online so that you can see them. But maybe I know there's some software and platform that maybe Alison can share the links in the chat, maybe for everyone, if everyone needs it now. Would be great. And your presentation, I think it was really amazing to see the development of the AI technology, and I think it's really interesting for our participants. Thank you so much. Okay, and our next speaker is from ESA. Let me introduce to all of you Dr. Nicolas Langevin. So his experiences, he worked in JAXA for the first 3 years of his career, and after that he has been working at CLS France as a research engineer in radar application division. Since September 2020, he is now with PhiLab Explore Office at ESA. His main scientific interests include Earth observation and star remote sensing and digital technologies such as machine deep learning. So, Nicola, you have the floor. Nicola, I think you may be muted right now.
Muted. Sorry about that. I'll show again my screen.
No worries. And thank you everyone for your comments. We will make sure to answer them in the AI. I see that some of the comments have already been answered, but I know there's much more things that could be explained orally. So yeah, I'll make sure to have everyone answer their questions again. So keep the questions coming. And also, please make sure before you leave the webinar to answer our questionnaire. Okay, I think things are ready. I'll hand it over to you, Nick.
Thank you very much for this introduction and this invitation. So I'm Nicolas Langevin. I'm with the PhiLab Explore Office, which is part of the Directorate of Earth Observation Program within the European Space Agency. So today I'll give a talk on AI and Earth observation, and we'll have some perspective with PhysAT1. So you all know that we are living an AI revolution. I mean, you all know about this self-driving cars, DeepMind, and also all the robots that pretend to behave like a human being. So this is for us some kind of new electricity. And actually, there is a convergence of three phenomena. So there is an overwhelming amount of data coming mostly from internet. You all know about this ImageNet database, which is based on actually from the crowd and from the people. We have also, as it was mentioned by Ellison and NVIDIA, we have an increase of the computing capabilities, mostly driven by Moore's laws, the fact that the number of the transistors in a dense integrated circuit actually double every 2 years, which is amazing. And also, we are available, we have now algorithms which are now available, made by big companies like Google, Facebook. We are talking about PyTorch, we are talking about TensorFlow, Keras, and so on. So all these three components are now joined, and we can do actually AI. Basically, within the Earth observation field, we mostly use computer vision capabilities. So we start from this challenge. I mean, we want to recognize cats and dogs from pictures. And if you want to do that, you build some kind of neural network. So this is the point that you see, and you put some artificial neuron, I will say. And at the end, you come up with the answer. Okay, you have a cat. You can even go beyond of that and eventually determine the species. So you can refine your classification scheme. Still, there are some issue with this black box because there is, for now, a trust issue preventing a wider adoption, I would say, in AI. This is an active field of research about fooling AI, meaning that if you add, for example, some noise that are not perceivable as a human being within an image, then the output of the algorithm will be totally different. So here, for example, if you add a banana over a cat, then maybe you will get a banana or a cat, you don't know. We are lacking also some explainability. We want also to integrate AI and physics all together. And we have also some bias in the methodology, meaning that if the database that you use as input is biased, then you will have probably some bias as an output of the algorithms. So anyway, still there is a big rise of AI for the Earth observation sectors. Actually, we start from this Earth observation community. So we have a bunch of satellites which provide terabytes of data. We want to use AI to get some new insight of the planet Earth. It can be about the land, it can be about the ocean, the atmospheres, and so on. So we are talking about El Nino impact, fire alerts, ocean bloom, whatsoever. I mean, there are so many challenges that humanity should face now and in the future that maybe using AI that blocks may help to get new insights. And actually, this is a real big rise within the Earth observation community. And here's the number of papers related to deep learning within the remote sensing community. And you see that it's definitely exponential. So people are using AI more and more within the Earth observation community. So it can be about many things. It can be about prediction, detection, classification, as mentioned with cats and dogs. It can be about big data analytics, enhancement, super resolution that was mentioned in the previous talk. It can be about emulation, parameterization, data science, process automation. Last but not least, I will mention that later in the talk about onboard autonomy and outboard, I will say, intelligence. So basically at ESA, together with the European Commission, we are part of the Copernicus program. So we build and we manage the data coming from different satellites. It is the Copernicus satellite, the Sentinel missions. So you have the Sentinel-1, which is a synthetic aperture radar sensor, Sentinel-2, which is a high-resolution optical images. You have Sentinel-3 for the ocean. You have Sentinel-5P for scanning the atmosphere. You have Sentinel-6, which has just been launched, I think, one week ago, about the ocean topography. And on top of that, this Sentinel mission, you have the Earth Explorer, which is, for example, Gauche. Gauche is for the gravity field. You have SMOS for the soil moisture and salinity. You have CryoSat for the cryosphere, Swarm. This is for the electromagnetic fields. You have also biomass. That will be a mission that will be launched maybe 2022. That will be about the biomass, for example, in tropical area. And then we have, for example, FLEX that will measure the photosynthesis. Anyway, you have this bunch of satellites. You have also nano satellites. You have also apps, which is high altitude pseudo satellites. You have also drones. You have also in situ and even social media. So basically within the Philab, we want to combine all this information, not only satellite, but also in situ, social media, internet information, combine all together to have new insight of the planet Earth. So basically we start again from this algorithm where you discriminate cats and dogs, but here you have a data cube, meaning that you stack all the data that you have from the different sensors. It can be, again, it can be Sentinel, but also Earth Explorers, can be also drones, whatsoever. So you take all these data sets, you put this into the network, and then finally you come up with a tangible solution, and you'll be able to discriminate crops, oil palm, ships, whatsoever. So in the following, I will just present you some study case. We are developing many of them, but here I will just give you an highlight of some examples. So here, for example, the challenge is to be able to recognize and monitor the infrastructure in the desert area. And for some specific region, you cannot use, for example, optical sensors. So you should use, for example, radar, which can penetrate the clouds. We can work day and night. So basically, in that challenge, we stack, for example, a number of data coming from the star satellite Sentinel-1, basically. So you prepare this information, then you collocate with some information that can be used as a ground truth. It can be, for example, OpenStreetMap, which is publicly available. And then you train a model, which is a UNET, which is some kind of CNN model, convolution neural networks. And at the end, you train the algorithm, and then you are able actually to recognize all this infrastructure, the road, the building, and so on. So this is an example using only synthetic aperture radar images. You can also do some kind of big data analytics, for example, count the number of planes within airports, and for example, this was some study case that we conducted during the COVID event, I mean, at the beginning. And also you can see the building change and the land use change, especially in the region of Wuhan. For example, you can extract all storage within all tanks thanks to dedicated methodology and also physical wear information. Lately, we have been working with WFP and UNICEF on, for example, on crop type detection and mapping in Malawi. So some camera just taking picture, I would say, on the crops. So we built some kind of neural network that are able to discriminate the different crop type from the camera. And then the idea of the project is, for example, to widen, I would say, the area. So basically with the drones, you have only it's only over a given route. And thanks to the Sentinel-1 or Sentinel-2 images, which has very wide coverage, more than 200 or 400 kilometers, then you can actually widen your prediction coming from the drone and let's say the situ measurement, and scale up to regional scales. So which is quite important, for example, to optimize, for example, the drone campaigns and to provide insight information. We can work also on generating CI chart. Basically, CI chart has been done by ICE Center. It can be from US, from Canada, or from Denmark, Denmark, Finland, or Norway, for example. So each country has some kind of national ICE service. But this service is actually provided by expert, by human. And so they have to ingest more and more data sets coming from different sensors. And now this is a new trend, meaning that with this kind of algorithm, this kind of CNN unit here, convolutional neural network, you are able to train what a human will do as a segmentation, as a CI charting. So basically, you take radar images. It can be also other sources of information. you stack all these images, and then you come up with some automatic classification that really can help to fuse the overwhelming amount of data that people now have, and that is very challenging for them to integrate. One aspect which is very important in the community is to work also toward spatial resolution, because some sense of, for example, let's talk about Sentinel-2, which is a free open. The resolution is only 10 meters, I would say. So it's not comparable compared to very high resolution optical images that you can get from private enterprise, which is less than 1 meter, 30 centimeters on the ground. But the thing is that these data sets with very high resolution are very expensive. So if you want to come up with say cost-free solution, you have to work on enhancing the spatial resolution. So basically, that field is very active, especially in the computer vision. So you have an example on the top left here. And basically, in the field of Earth observation, this is a really active topic, and how you combine different sensors having different revisits and eventually better resolution. We are working also on some specific challenge and combining, for example, the radar images, which are working day and night, and also whatever the cloud condition, and also with Sentinel-2, which is an optical sensor. So you are dependent on the cloud condition. So we are building some kind of intelligence, artificial intelligence based, for example, on generative and adversarial network, to be able to synthesize what would have been the Sentinel-2 free cloud images. So you train from the stack of Sentinel-1 and Sentinel-2 images, and if you have some missing data due to the cloud, then you are able to rebuild the information thanks to the radar images. So this is some kind of topics that we are working on. A last point, which is about emulation and physics. For some specific sensor, you have to consider, let's say, radiative transfer model, so basically physics. But for some specific example, sometimes it's very computationally intensive to use that model because it's too huge. And if you want to integrate new parameters, it is also very costly. So basically, the idea is to build some kind of neural network that are able actually to mimic what will be the radiative transfer information. And sorry about that. And it was successfully applied on the tropomy spectral, which is used to retrieve, for example, the methane information. We are also building some tools to help people to use AI and Earth observation imagery. It can be annotation tools. It can be, for example, application on smartphone. This was developed within the frame of the game.io project. The idea was to present some images, and the user will have to decide yes or no, do you see a slum within the image. Whereas if you talk about AI, it's important also to build some ground truths and to have some kind of training data set. And to do that is sometimes very, very difficult. One way to do that is to involve actually the clouds and the people to do that. And we are working on a specific project to actually do some kind of gamification. So you enter you have a video game, and thanks to that video game, you have multiple players. And actually that within the game, the players will actually annotate some data for you and will give you then some training data information that can be used for the training. So this is some new way to get some annotation. We are also building some tools that directly, directly take the data where they are. So meaning that most of the data are now on the cloud. So you need to have some powerful algorithm and powerful tools that are easy to use and that are easy to extract useful information, whatever the place where the data is. So we are working with some partners, and you may look at this initiative EO-Learn, which is very useful to extract, for example, series of Sentinel-1 or Sentinel-2 images. We are developing also some toolkits for users which are not expert in, for example, in the SAR domain, use that information and to create some stack of images. So you have the link to the GitHub here. Last but not least, and I will mention about artificial intelligence at the edge because, and I quote here Peter Platzer at the FEE Week 2019. I mean, the value of the satellite-based Earth observation no longer grows with the ability to collect and transmit data back to the Earth, but it's increasingly lies with the ability to transmit customer relevant insight in near real time or in real time. So we want to provide us information as soon as possible. And so in a sense, we need to have some kind of BrainSat that will put some intelligence directly on the satellite and then transmit the right information. And in last September, I think it was on the 3rd of September this year, actually ESA together with some industrial partner launched the FEESat-1, which is the very first satellite, which is a CubeSat, having AI chip on board. So actually FEESat was an enhancement of the FFSCAT mission. So with different payload on board, so you have a GNSS radiometer and also an hyperspectral sensors. The issue with the hyperspectral sensors is that you have multiple bands. So to transfer that information up to the ground, I mean, it is very demanding in terms of bandwidth. So basically you cannot do that. So the idea of this mission actually was to put an AI chip which was able to recognize where are the clouds. So where are the useless information that you don't want to transmit to the Earth. So we put actually an Intel Movidius Myriad 2 sensors on VPU on board. So why? Because it was quite fast, and also it has a low power consumption, and it was quite small. You can see here it's just you can take it in a hand, so it was very tiny. So to conclude, AI really can accelerate the time to get some new insight of the planet Earth thanks to Copernicus data, but not only. And more than that, actually, I can help actually to learn, let's say, some underlying structure of the data and to discover new aspects. So I think this is all for me. Thank you for listening, and if you have any question.
Thank you so much, Nicola, for your interesting presentation about the activities done in ESA. It's really amazing to see how AI is getting incorporated into all the space activities that are being done. And I think it's amazing. And I hope all the participants here were able to take some insights and maybe collaborate with ESA in the future. So thank you so much. Okay, so we have a lot of questions going on in the chat, so I'm going to try to have them all answered now. So I guess the first question is to Jorge and me, which is how to work together with UNOOSA and the Access to Space for All initiative. Maybe Jorge, you can add something as well. But also, if you can connect, email us directly, we are always happy to engage. So maybe I'll just write in the chat our email address as well. Jorge explains. Yeah, go ahead.
Yeah, well, there are many ways to engage with the office in Access to Space for All. I mean, on one side you have the applicant side, and you can apply to the opportunities and benefit from them. On the other side, we have partners that are providing opportunities. We work with partners to make sure that these opportunities are for free, and they are usually in-kind donations from the partners. Also, another way you can help us is basically raising awareness about the initiative, to get the initiative to the people that can benefit from it. And that's why it was important, the use of the hashtag and to spread the voice. So we'll really appreciate any collaboration and any help that you can give us. Thank you.
Thank you, Jorge. Okay, I'd like to move on to our next question, which I'm trying to find. I think it was a question about how to work on AI in a developing country. So maybe I can start with Allison. Do you have any advice on where to start on how to work on AI in the non-developed countries and new countries that really want to start working on AI?
No problem. There's actually the wonderful thing about AI is It's all based on code. You can do anything via an internet browser. So long as you have an internet connection, even if you don't have any capability at home, you can go to a local internet cafe and you can start learning. We have classes. Many people have classes. Stanford has been putting out university, class data and full courses for many, many years. And the great thing again about artificial intelligence, which probably adds to the fact of its unprecedented progress, is the fact that everything is shared. Let's say 99% is shared, the various defense applications, of course not. But that means the code and the papers. So archive, so that's ARXIV, Google Archive, that is where everybody publishes every scientific paper for peer review, whether it's a work that is on stage at the biggest conference. For example, NeurIPS is happening next week. They do charge to actually get most of the data, but if you follow many of the researchers on Twitter, or for example follow me, because I'll basically be tweeting out a lot of the really profound stuff that's coming out of NeurIPS next week. But code really is something that anybody now can learn online, whether, as I said, that's at an internet cafe or in a high school or in a university, if you're able to do that. And a developing country and a developing country's government should be pushing that. And to be honest, we have a huge initiative here called AI Nations at NVIDIA, where we're working directly with governments. And I can happily introduce anybody to my colleagues who are working on the AI Nations strategy. So that's AI, the infrastructure that's needed, space hubs, for example, 7 more have just been announced in the UK. I've put my details in the chat, just send me a message and I'll help.
Thank you, Alison. Can I ask you the same question, maybe Colin and Naeem from IBM?
Yeah, so I think Alison, she explained very well. There is so many resources available right on the web now, and like, for example, someone just posted the ARX5 or 4.org, right? There's plenty of white papers available there. And then and NVIDIA and IBM and other companies, there is so much like AI related stuff available on the website. So I think you just need to do a little bit of searching, and all you need today is a laptop and a connection, and you can go and learn stuff.
Thank you. Colin, do you have anything to add to that?
No, I think that they've covered it rather well. And I know that some other companies, especially Google, have made sort of hardware resources available too. So you can use Google's Colab environment to get access to a GPU, so that you can, actually implement some of these things in a notebook environment without having to. They offer that for free.
Yeah, there's a huge initiative been going on now for a couple of years in Africa called Deep Indaba, and that was started by a DeepMind researcher and folks from the NeurIPS conference, which is the world's #1. And part of that is that anybody can access Google Cloud for free with our older generation GPUs. And this may come as a surprise to any non-coders in the audience, but you can literally from your laptop log in to a setup that has huge amounts of storage, huge amounts of GPU compute and devices, and perform artificial intelligence. Most of my research was done from my bedroom at home in university, not in the actual lab, for the simple fact you only need an internet connection to then tunnel through to all these capabilities, and that's what we call the cloud service providers. But Google has provided it free for the older generation GPUs, and that's perfectly capable for what you need to learn, certain applications. And we literally will walk you through those in our classes.
Thank you, Allison. Yeah, and right now it's locked down in some countries. People have time, but if you have the internet, it's a really great timing to, I guess, work on AI because you really don't have to go to the lab, as everyone was mentioning. So, yeah, thank you for your answers. And yeah, I'd like to ask the same question to Nicola as well. Do you have any thing to add?
Yeah, sure. I mean, I will have more or less the same remark than the previous speaker. So we have the available algorithms which are now published, and you have also the GitHub, which are full of example, and you have also some tutorials. You have also Medium, which is some kind of general media for AI stuff, and also you have the data which is free. I mean, you can look at all the data generated by the space agency, for example, ESA, but also in the US, you have the Landsat archive available. At ESA side, you have all the Sentinel-1 made available by the Copernicus program. So you have the data, the algorithm, and also the infrastructure with Colabs or Google Earth Engine. So I think there's no barrier to use AI on Earth observation, for example.
Thank you so much to all the speakers for your answers. Okay, the next question is, how do you get information about these kind of webinars? So I guess Jorge already answered in the chat, but please make sure to answer our questionnaire. And at the end, there will be a question about giving consent to us about your email address. And when you do, you will be added to our list, and we will send you a lot of information about our webinars, activities, and stuff related to maybe AI. So yeah, please make sure to answer our questionnaire. Okay, next question is to IBM. I saw Naeem and Colin already answering it, but yeah, I'd like you to explain because I know chat is not enough. So question to IBM, I would like to know more about blockchain. How do you see the future of this technology for Earth observation data accounting and authentication?
Sure. Like I mentioned in the chat, right? So the major use cases for blockchain, besides the logistics optimization, is also about the providing the transparency into the process. And this is when you're doing data sharing, and there is a lot of Alison, we can all agree to that. Many of these large companies, the data is being produced so much, they want to monetize this data, and that's where you bring blockchain in. So you have a buyer and a seller, and you can see what they're selling and who is buying it, and you have full transparency where data is going. So yeah, I mean, blockchain can play a huge role in sort of a data marketplace where not only you sell your data, but you can also maybe sell your algorithms and you can monetize them.
Thanks so much. Okay, I think I'll move on to the next question, which is for Allison. Maybe you already answered them, but take your time to answer them here. Which are the skills that you would recommend to put all that work together and to get all the power, get all the power of AI? So where should I start from? It may be similar to the question before, but yeah, if there's anything, Allison.
Sorry, I was on mute. So coding is essential. Folks don't quite realize that there's so much hype and talk about artificial intelligence, which is a huge field. And, it includes a ton of things like natural language processing, robotics, etc., etc. But everything comes down to code. So first of all, you need to learn how to code. And there are hundreds of classes online, free classes online that you can do to actually learn code. Python is probably the most important one, I would say. But others would argue for the most fast, most efficient, it's C or C++. So learning to code, first of all. From there, take a look at all the resources online. Read a scientific paper, and for all those bits of it that you don't understand, start looking it up. Google and the internet now have so many resources for anyone, so long as you have an internet connection, and that's really the basic requirement. It's like air to breathe for me. So start coding, and from then it's really very, very simple, because if you can understand how to do a pull command, from a command line, then you only need things, repositories like most papers come with code already, so you can reproduce, and that's the purpose, is so that anybody else can reproduce the code and get the same results. But you only need things like that, and the repositories like the NVIDIA GPU catalog, where we've already written the code, we've containerized it to make it very, very simple to just pull down the code and start running, start deploying across so many different kind of applications already. And again, you know, IBM's done so much to help people along here. They have huge amounts of resources from their website as well. And ESA, of course, the Copernicus, the outreach side of what ESA does is incredible. So there's a lot of help out there. But first of all, just learn how to do a simple Google search and to code.
Thank you, Alison. I'd like to ask the same question to Naeem and Cohen also, and maybe if there's any IBM things that you recommend. Yeah, go ahead.
Colin, go ahead.
Yeah, no, I mean, I would, you know, echo Alison's comments on, you know, code is key. It is lingua franca in the space. It is sort of like step zero, I guess. You know, yes, in IBM, we provide, you know, a notebook-based environment that you can use to get started with these, you know, learning how to use Python and all of that. So I off the top of my head, I don't know, but I can pull together some of our resources that we make publicly available and share that with Jorge.
But as step one, right, like everybody said, just start with Python, right? If you're just beginner, just start with using Python, and then things will open up for you. Yeah.
Thanks so much. Nicola, do you have anything to add, or is it start with Python? Or...
Yeah, start with Python. That's the basis.
Okay, thank you so much.
I would like to say I was actually active. I was a teacher of teachers. So that's teaching primary school teachers how to teach code, and you know, concepts like what is an algorithm. It's basically like a recipe, that kind of thing. So primary school, I'm a big believer that we should be teaching, you know, primary school level code now, and it really is quite simple. When you don't know how to do something, especially, you know, as we get older, we think that it's even more and more impossible. It's really not. Code is actually, you know, at the primary level of just being able to pull down the code that you need is actually quite a simple thing. And that's one of the great things about our Deep Learning Institute classes, which use something called a notebook, where you're literally just reading almost like a book, but you're running code just with, you know, a click of control and enter. So it's really quite interesting. And until you do that, you don't really get the whole concept behind it.
Thanks so much for all your answers. I guess I'll start with Python as well. Okay, the next question is to IBM. I was wondering if the SSA open source project was collaborated on real data. If yes, could you talk a little bit about the strategy? So maybe you answered in the chat already, but if there's anything you want to add here, go ahead.
Yes, for the SSA project we shared, yes, we use the open source version uses real data from spacetrack.org, which is provides TLE data for all of the objects in the low Earth orbit catalog that they track. And so we use historical versions of that to create our training data. And then we, you know, calibrate that on, we use current TLEs that come in to then be able to do, you know, do real-time monitoring of our algorithm to make sure that it's, you know, it's working as expected.
Thanks, Colin. Okay, I guess we'll move on to the next question is, and I think it's for all. So, okay, sorry, my chat froze for a second. Okay, great. How do you ensure AI is doing the right thing? Because that I have the same question. So how do you ensure AI is doing the right thing? Is it not too dangerous to use in satellites or in SSA systems without really knowing what they do? So yeah, please enlighten us all with this question. Maybe I can start with Nicola.
Yeah, that's a very important issue that we face also in the Earth observation sector. So what we do usually is before the launch, for example, in the case of the FISAT, there was some preliminary experiments. So we compared different solutions altogether using AI and more, let's say, more machine learning based or traditional algorithms. So we do some benchmarking, we do assess. For sure, there is, as I mentioned in my talk, there is some bias. If you have a bias in the database which is used in the training part, then you will probably have some bias in the output. So there may be some lack of representativity. So adding some physics prior within the networks might be a solution. Doing benchmarking, also assessing the robustness of the algorithm. This is some stuff that everybody should do, I think, and that can be part of the solution. Also, trying to see within this black box is an active, let's say, research field. I mean, people are trying to provide some solutions to get some attention models, some stuff like this. So this is an active field of research as well.
Thank you, Nicola. Maybe I can have our IBM colleagues answer this question as well.
Yeah, so I mean, there are kind of like several steps to it. First, is in kind of the training process to make sure that, you are doing your training correctly and, maybe not overfitting to your data, so that it generalizes to things that it hasn't seen. And then also is kind of, monitoring in production. So how do, and that's what we're doing now with our SSA algorithm, is to ensure, like, when we get new TLEs, how after we've seen the next TLE, how well did our model perform previously? So we're constantly monitoring how well it's doing in production, so that when we see anomalies, we can go back and say, okay, oh yes, we didn't account for this in training, just because, like was said earlier, there was like a lack of data in this area, so something we couldn't really have foreseen a lot of. So it comes down to, I think, a two-step process of doing your training correctly, but then also monitoring the production.
And just to add that to, a very fundamental step here is where this data came from, right? So we are building this algorithm for solve a specific problem. What was the source of this data? Who built this algorithm? What went inside building these algorithm recommendations? And then, like Colin said, constantly watching for the output. And it's like a loop, right? You're constantly looking at it. So these are some key fundamental things to make sure that, it's doing what we want it to do.
Thanks, Naeem. Yeah, and Allison.
Yeah, so human in the loop. This is absolutely essential. I put this in the chat earlier, and there's a huge amount of work being done on this. We have a vast amount of people focused entirely on self-driving cars, which, aside from space, is the ultimate mission critical application of artificial intelligence. And human in the loop is an absolute necessity. Interestingly enough, as I mentioned in my talk, we can use simulation. And the really important thing about simulation is that you can generate all kinds of possibilities, or what we call corner cases. And that's beyond what a human would ever consider as a corner case. It's all the things that that we think we could think about, but actually, more importantly, that we would never think about. And you can actually generate that in a simulated environment. And it's an important part of human in the loop to have that capability of, superior to human, let's say, design and the creativity side of things, plus the actual real world. And the combination of simulation and real world is actually more effective, more performant, more accurate than just real world, plus the human. I personally don't believe there's any need for full autonomy in any mission critical situation. And, to go to the absolute most controversial, that includes weaponry. there is some kind of automation that is justified. But at the very end of it, it should be, and AI should always be just to assist human beings. That's where the power is, not to replace us, because the combination is, phenomenal. And let's face it, that's why we created AI.
Thanks everyone for your answers. It's really interesting. The next question is a bit similar maybe, but it is addressed to Allison, but I want to ask all the speakers here. So the applications and projects on AI in space are game changers as they can catalyze deep space exploration. So it is a matter of time that AI will be used during human space exploration missions such as Lunar Gateway, Artemis, and other projects. So in your opinion, how do we ensure that some of the biases in AI we see on Earth do not get replicated in space? I think it's a bit similar to the earlier question, but to focus more on space exploration to fill in all the gaps. So maybe, yeah, I can start with IBM. So Naeem or Colin?
Sure. So I think AI will play a huge role in this space, and it's already doing the work which we are, Allison and we all work together in the NASA FTL program. If you just go on frontierdevelopmentlab.org, you will see for the last 4 years, a bunch of projects which we are looking for the deep space exploration. But you think two things come in mind, right? The Artemis program, which is going back to the moon, the Lunar Gateway in process, and then going to the Mars, right? I think last night, Alan, he mentioned that in 2 years, we can see a non-human flight to Mars, and in 4 to 6 years, humans, right? Initially, it will be all robotics and AI, and robotics will be driven by AI, like the cool simulation Alison was showing, right? This will play a huge role in going over there and understanding the environment and making it ready for the humans to arrive. So I think it will play a huge role. And the way you don't want to repeat the mistakes again, it's like human in the loop. In this case, it will be virtual, like the digital twin, we can say, and then continuously watching what the AI is doing.
So just to add to that, I think it's sort of inevitable. You can't really do deep space exploration without this because the farther you get away, just the lag in radio communication with the ground is just going to be too much to be able to do a lot. So you're going to see, a lot of this come up for maybe mission control or diagnostics and repair as well. And so how do you sort of prevent biases? And I think an area that you're going to really see a lot of come in play here is sort of reinforcement learning, of where the algorithm is kind of continuously updated based on its environment. So it sort of will wash away any maybe training bias via sort of its interaction with the real world in performing kind of those tasks.
Thank you. How is it for you, Allison?
So to focus on the bias side, I would honestly say that the work that we're doing here on Earth is extremely important. We're in a very, very nascent stage, we're in its infancy, and we're learning, just as the whole species is learning about artificial intelligence. We'll learn more and we'll develop more and we'll get it better when it comes to bias, to any kind of bias. We have so much bias already with, just between humans, that as we're learning, we can very simply put that into the code for artificial intelligence, for artificial humans. So far as deep space, it's really more about the engineering, and there's no need for any kind of bias if you're talking about the emotional side, the human side, because a robot will be given, or a spacecraft will be given an objective, or an AI application will be given an objective, and it will do that. And if it doesn't do that, we'll go back and we'll do more development on the code, and we'll get it even more accurate until we hit 99.9 or whatever the approved figure is for accuracy in that. The deep space side, especially the robotics, is very simple. With, for example, route planning, going A to B, and using distributional reinforcement learning, for example, for that robot to autonomously plan how to get from A to B and to then drill, for example, into the rock. The the real problem of bias doesn't really come into those kind of pure engineering applications. Ultimately, when we are much more developed in deep space, and we have a robot that is to be a true artificial human, will have already got, and I strongly believe will have already got to the stage where we have acceptable bias, just as we have acceptable bias in the AI applications we use here on Earth.
Thank you so much, Allison. And I'd like to ask the same question to Nicola as one of the major space agencies.
Yeah, to complement Alison's comment, I will say that in the field of Earth observation and then observation of meteorites or other planets within the Earth, or on the Earth, I mean, this is all logical that first we need to build up the system for the satellite around the planet Earth and do Earth observation, I will say. And then in the next phase, when all this field will be mature, then there will be no issue to put that sensors, for example, scanning asteroids or scanning the planets, that's Mars or the Moon. So I think that we need to be pragmatic and be step by step, and start at least with AI on board for Earth observation, and then we'll go for the deep space exploration and do deep space observation.
Okay, thank you so much for all your answers. The next question I think is to Allison. So is FDL open for participation from students?
Yes, it is. I put in the chat the link. The next call will be probably January. At some point in January, we'll open the call for the Summer 21 program. Anybody, so long as you're a PhD candidate, a student going through for your PhD or above, can apply. And then there's a whole NASA ESA candidate selection process that happens. And again, as I put in the chat earlier, we're always very proud of the fact that we hit at least a third female to male ratio, which is pretty good for this year in the entire tech industry.
That's wonderful. Yeah, thank you. I guess the next two questions are for Nicola. So is ESA releasing these models and documents for people to use them? Given that ESA funding is public, it would make a difference. And also maybe the next question too. So we have greater challenge in hydrometeorological disasters. The post-damage assessment is difficult task due to cloud cover. So any advice? So yeah, Nicola, if you can answer these questions.
Sure. Regarding the first question, for sure, I mean, we push for an open data and open source policy. So as long as we can, I mean, when we work with partners like universities and public organizations, usually that's not a big issue to have this policy with them. But you have to remember that ESA also found and in European service industries and space sector. So we should aim to accelerate the competitiveness of this industry at European level. So for some specific case, the model will not be disseminated because you have some kind of background intellectual property rights, some stuff like this. So that might be some specific cases, but generally speaking, we do promote open source. So this is, and if you have any interest in the presentation I mentioned, I mean, please email me and I can guide you with some open source codes or open source open data set that we release. Regarding the post-damage assessment, for sure, the clouds is a real issue. So working on technologies such as synthetic aperture radar might be the solution to come up with a cloud-free and a sensor which is able to work day and night as well. So combining, as I mentioned, optical sensors and also radar sensor might be a good fit for this damage assessment. And also, yeah, now there is another trend about some new space company who are building small site synthetic aperture radar, which enable eye revisit. So you may have very frequent SAR images with high resolution. So you have new players in US such as Capella. In Europe, we have also iSize. In Japan, SyncSpectile. So new players doing some very high resolution and very high temporal visits, synthetic aperture, or other constellations. So that may be a good fit for the post-damage assessment as well.
Thank you so much, Nicola. Okay, our next question is, can we apply emotional intelligence 100% using artificial intelligence? Naeem, I see you're smiling, so I'm going to ask you to answer it first.
No, I was just, I have not thought too much, but I think Alison, she replied, right? But I think it's a facial recognition, right? There is some challenges that I think we actually, from our company's point of view, we got out of it. And it's a very tricky thing. So I will let anybody else who wants to answer this question.
We're doing lots in this space, actually, particularly voice. So for self-driving cars, for example, it's really important that you have voice command capability. And without naming too many names, there are large space agencies also doing this for their spacecraft. So voice command is really interesting, and that's let's say, just to very simplify the question, half of the problem. Understanding nuances in language is quite difficult. GPT-3 this is again a chat thread that's a conversation. That is an extremely capable model, but it's still not perfect. And again, brings back the whole point of Hill, human in the loop, to actually train this. And a lot of people are bringing humans into the training side for, let's say, robotic helpers. How do you get around those nuances? Think about when you're asking your mobile phone by voice a question, the mistakes that it makes. That's what I mean by nuance in language. The other side is sight. We have 5 senses. Smell doesn't really come into it. Touch definitely comes into it in certain robotic elements. But the sight and of course sound is voice. But the sight sound is the other half of the very simplified problem. And to be able to see nuance of human behavior is really, really important. And we can pick up emotional intelligence when we're, for example, looking at somebody's eyes. The capability of AI in vision applications, vision-based applications, is far superior to human beings. However, we still need Hill, human in the loop. For example, in the airport, when it's picking out certain people to get around that bias or the potential bias in the training data. And emotional intelligence, again, just comes down to us perfecting the code and the applications. And again, that comes down to perfecting the training data that we're using. Let's have a broad coverage of all populations. An example with health was certain applications that were looking into cancer applications, cancer cases, hadn't taken into account enough Latino people in their data. And so there was an entire almost population of people that weren't accounted for. But that again it comes down to the fact that we're in a very nascent stage. We are learning as we're going, and I would say AI research is catching up with the human psychological research that we're all going through about learning about this, emotional intelligence, what that means, and getting over any biases or unconscious biases that we have.
Thanks, Alison. Nicola, did you have something to add? You're muted, yeah.
No, sorry, nothing particular to add.
Thanks. Okay, I see a lot of people already writing in the chat, but the next question was any book you can recommend on AI, and also if there's a database of space-related AI applications. So I know you, a lot of you have mentioned some of these, but if you have any that you really want to emphasize on, here's your time to let everyone know about the book or database. So maybe our colleagues from IBM, do you have anything you want to emphasize on? Any books, database?
Yes, I'm not really aware of any database of of applications that for specifically looking at space. But I would look at maybe some of the space-related conferences. That's where we have found sort of relevant materials of how these are being applied.
And the interesting thing with artificial intelligence is it's operates at a mathematical level. So the code for a vision-based object detection algorithm is the same. It's exactly the same whether it's for a space-based application or a car-based application or a mobile phone-based application, with certain alterations for the actual mode that it's working in. Obviously, it's got to be much more performant, much less power for a mobile than it has for a spacecraft, for example. But for that reason alone, the application side, if you want the code, go through any of our Deep Learning Institute classes on object detection, or pull down any of the object detection code from the NVIDIA GPU catalog, because it's already written. And you'll be able to use that. If it's for the actual use cases, as in a list of how you can use AI for space data, for example, ESA actually put out a fantastic document, I think it's about 2 or 3 years ago now, on 99 use cases of space data. And it's, I'll see if I can find the link and I'll add it to chat now.
Thanks. And Nicola, I see you writing on the chat, but
yeah, I think that the first book that I mentioned, the Python Machine Learning by Ashka, is a really good book because it's quite simple. I will say there's not too much theory, a little bit, but it's more practical and pragmatic view of doing machine learning and deep learning. So it goes step by step, and it increases the complexities of the model, starting from very basic one, from Bayesian scheme or something like this, up to complex deep learning. So I think that's a good start. And then the second one I was referring, deep learning by Goodfellow, is like a more theoretical basic background. So you might need to have more mathematical background to read it, but it's like the basis and the Bible for all AI and deep learning guys.
okay, thank you so much for everyone, for the speakers, for your answers, and for the crowd for engaging with us with your questions. So I know there was a lot of information. We'll make sure to share the links of the information we have here on our website later. We'll make sure to share the recordings and the presentations as well, so that you can share it with your colleagues who were not able to join in with us. So yeah, we'll try to do that definitely by next week. So yeah, I guess this is the end. I really, really am happy to see that there was a lot of engagement here. So thank you so much for all the speakers for your cooperation, and thank you all for the speakers for coming in. For the speakers, I want to take a little photo at the end. So can you stay for a bit? And for everyone, please make sure to answer our questionnaire to get more information. And yeah, we'd like to hear your feedback. And also we have more webinars coming up. You can check all of that on our Access to Space for All initiative page. So thank you so much, and I hope you enjoyed it. Okay, for the speaker, everyone smile at the camera. Okay, I think Jorge, you got it? Okay, great. Thank you, everyone, for your time.
Thanks, everyone.
Thank you, everyone.
Thank you.
Have a great day.
Bye.
Thank you, everybody. Thanks a lot.